All right, so last section we're going to look at is same one we did yesterday, 11.2, just the second part. So yesterday we discussed a series. Okay, what is a series again?
It's a sequence of numbers that you add up.
Yeah, it's the sum of a sequence. Yep. So the kind of series we looked at yesterday were finite. What does it mean if a sequence is finite? It ends. There might be 10 terms in it, there might be 1,000 terms in it, there might be 1 billion terms in it, but it ends somewhere. Okay? It ends, we usually said it ended at n, where n was a positive integer. Well, today we're going to look at an infinite series. So an infinite series has no end. It's a sequence of numbers with a dot, dot, dot. It goes on forever, and you're adding them all up. So one idea is it's kind of hard to kind of wrap your mind around a little bit, but there's this idea, can you add up an infinite amount of numbers and actually get an answer? Okay, I mentioned that earlier. And it depends. It depends on the kind of numbers you're adding up. Okay? But certainly, we can't add up an infinite amount of numbers by hand. Right? I mean, even if you wanted to add up 1 billion numbers by hand, you can do that. I mean, a computer can do it faster. But infinite, we got to come up with something else. Even a computer can't just keep adding things up forever. It would never give you an answer. So there's got to be a way to do that if it would come out to an answer in a way we're not thinking about. Okay, so that kind of answers the question that I just asked you. Yes, there are some series that when you add up infinitely many numbers, you get an answer. Or you get closer and closer and closer and closer to an answer. Anybody remember where that idea came up earlier in the year? Like something getting closer and closer and closer, but never actually touching it? Like an asymptote, okay, or what we call the limit. It was a number that you could get closer and closer and closer to, but you never actually reached it. You only reach it at infinity. Okay. Okay, anybody else up with that? So the notation for an infinite series, it's just like the sigma notation we used yesterday, but you don't put an n on the top. You put the infinity symbol. And when you expand out something that's written in sigma notation, you have to end with a dot, dot, dot. If you don't put a dot, 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 you just made it finite. It means it stops. And this idea I already mentioned to you. It's not possible to add up an infinite amount of numbers by hand directly. So we're going to have to think about doing something else. And then what we're going to think about, the first way we're going to think about it is visually. Okay? We're going to almost think of like graphing the sequence. And we're going to see that the sequence gets closer and closer and closer to something. Just like an asymptote. All right, so now I'm going to just go through and kind of explain what we were saying about the idea that if you approach a certain number, it's going to act like an asymptote. That's going to be the answer to our problem. Right? So basically, if there is some number, s, and I'm using s because s would represent sum. Like sum, S-U-M, adding things up. Okay, so if there is a number s, and you put a horizontal line at y equals s, and that line is an asymptote for your sequence of numbers. All right, so let's say you had a sequence of numbers that looked something like this. And you draw a horizontal line like that. And let's say that that line was at, doesn't really matter, y equals 2. So horizontal line 2 units up from the origin. If you graph the terms in your sequence, and the terms in your sequence are going to get closer and closer and closer to that line, so that line is a horizontal asymptote, then we say our sequence is converging. Okay? What's it converging to? It's converging to that line. Converging just means it's getting closer and closer to it. And that line is going to be at a specific number. In my case, I just made it up. It's at y equals 2. So I would say here that my sequence is converging to the number 2. And 2 would be the sum. Okay? That's the number that these are approaching. Now, I put my graph as dots. Why did I do dots? Why didn't I connect all these? Think of those dots as terms in a partial sum sequence. They're individual terms. Why don't I connect between the terms? Yep.
Because like if you made that into a line, it means all the points on that line would be part of that sequence.
And why can't there be something in between the dots?
Well, because
for terms?
It's a certain pattern. Like it's just what it is. Like it's only those numbers. You know what I mean?
Yep, it is only those numbers. Why can't it be between them though?
Because it's not the values in between.
Nothing exists between them, right? If you have a first term and a second term, there's no 1.5 term. There's nothing between them. That's why I put second term, third term. Nothing between them. Right? So again, we say that our sequence is converging to that number. It's getting closer and closer to that number the closer you get to infinity. It might not be close to that number at first. Like this dot is way up here. It's not even near the line. But as you head further and further to the right, towards infinity, it will be. So it's a little wordy to write down, but it's not an overly complicated idea. It's just think of a graph approaching a line. Whatever number it approaches, that number is the sum of our series. Okay, so the first one I do, I'm going to graph it. I'm going to graph a sequence of partial sums. So in other words, each dot is going to represent a sum. The first dot will represent the sum of the first term. The second dot will represent the sum of the first 2. The third dot, the sum of the first 3. The fourth dot, the first 4. The 50th dot, the sum of the first 50. Okay, if you look that far out, by the time you've added up the first, probably even the first 10 terms, you're going to start to see the pattern. Usually you don't have to go very far to see what the sum is approaching. All right, so get all that. Okay, that, you don't really need to copy that down. That's just, this is an infinite geometric series, and I've expanded it out. We're gonna do it right here. Now, I haven't given you a formula yet to do this. All I've given you is a suggestion about trying to graph something. So we need something we could graph. This is a geometric sequence. How do I know? Because whenever you multiply by a number in front, that's geometric. If I had something like that, I would say it's arithmetic because I'm adding a number. Okay, multiply by a number, geometric. Adding a number, arithmetic. So I want to write down two things. It says to get the first term, let k equal 1. Let's plug in k equals 1 and write down the first term. What's 1 minus 1? 0. And then 1/3 to the 0 power. 1 times 2. So really the first term, and if you look up above, it tells you that the first term is whatever is sitting right here. You don't even really need to do out what we just did. And what's r? 1/3. R is whatever is below the exponent. Now, yesterday, did I write it down here? Yeah, yesterday we had a formula for figuring out the sum of the first n terms. I want to plug that into the formula, and I'm going to graph it. What was our formula? A1.
1 minus r
Yep, 1 minus r
to the nth
to the nth power,
power.
which in this case I'm going to fill in r. R is 1/3. All right. Divided by 1 minus r, which is 1 minus 1/3, 2/3. So I've done this out for a couple terms. If you wanted to do S sub 4, I just took the formula we just wrote down, and I plugged 4 in for n. Okay, and if you do it all out, you get 2.96. What I can also do is type it in on the calculator, and that way I could just use the table, and I wouldn't have to keep typing in the number by hand. Okay, so I'm going to put that into the table, but we got to just be careful with parentheses. So 2 times, let's try it like this. 1 minus 1/3. So I'm going to close the parentheses for the 1/3. I can't use n. I have to use x on the calculator. And now I'm going to close parentheses for the numerator. I think I'm good. And now I'm going to divide, open parenthesis for the denominator, close for the denominator, and then close it for the entire thing. So I have 3 parentheses opening 1, 2, 3 to the left, 1, 2, 3, 4 to the right, so I probably need 1 more. Oh, I already had 4 to the right?
Yeah, you should be good.
1, 2, 3, 4, 1, 2, 3, 4. Okay, yeah, that should be good. Okay, let's type it in the table. If we get 2.96 when you type in 4, then we know we're good. Okay. Then I did it for 5. I got 2.9877. So if you add up the first 5 terms in this sequence, that's what it adds up to. If you add up the first 6, you get 2.9959. So what do you think if you added up an infinite amount of terms? Well, what's it getting very close to? It's getting very close to 3. And the way we could see it visually is on my calculator. We're not going to look at adding up negative terms. Let's just go adding up the first 20 terms. And I know it doesn't add up to more than 3, so I could set my y max at 4. Okay. What that line represents is all the partial sums. And you want to think of it as dots. I can't draw it as dots, but that's what it should be. Okay. So if you trace along it, that's what you get when you add up the first term. 2. When you add up the second term, 2 and 2/3. When you add up the first 3 terms, first 10 terms. Okay? Even when you get to the 10th term, it's already 2.99999. So if you see that, you can basically guess that it's approaching 3. Okay? So I'm just showing you visually how quickly it approaches 3. You don't have to add up that many terms. And it looks like it's perfectly flat. Is it really flat? No, it's going up just slightly. Okay, just barely going up. But the calculator doesn't have enough detail to show that.
You could draw those dots.
I don't think it'll put the dots on the,
It'll just be really close together, but it works.
like if you do something like
Yeah, it
that,
works.
what's going to happen though is it's not going to put dots every integer. It's just putting dots wherever it wants to.
Oh, really?
Yeah. I only want to put, like these dots shouldn't exist.
Okay.
There's only one dot, and it's at x equals 1. The next dot should be at x equals 2. I've tried doing something like this, in parentheses, putting the, no, you can't, yeah, there's no way to tell it to not try decimals.
Okay.
At least I don't know how.
Could you set the X thing to only to like 1? You know how like maybe,
Well, you could set it in the window, like you could set the X scale to 1.
yeah.
So, and you could set, actually you could set delta X to 1. Trace step is 2. Let's see what that does. All that's going to do is affect, yeah, actually, did that do it? No, I'm not sure. It doesn't, when I trace now, it's going by 2s. See the X values? But the thing is, I think if I were to type in like 111.5, it would still go to that point, even though, or 11.5. Yeah. There's no such thing as the 11.5th term. There's an 11th and a 12th. So I'm not sure how to do it, but that's okay. You don't have to worry about that. Okay, so any questions why this one is approaching 3? All right. So I already said let's visualize the sequence. We already did that. So to visualize the sequence, you type in this formula, and that's exactly what I did. But I filled in R, and I used X for my variable. Remember to focus on positive integer values. Plugging in 12.3 for X makes no sense in this problem. You can plug in 12, you can plug in 13. You shouldn't plug in anything in between. It has no meaning. And then as you let X get bigger and bigger, let X head towards infinity, that's a good approximation of what an infinite amount of terms will add up to. And by letting X head towards infinity, you don't have to go that far. I can go to the 10th term in that picture I showed you, and I can tell it's 2.9999999. So I can tell it's not going to go past 3. Okay. So any questions on that idea of how you can use the formula we learned yesterday, graph it? You got to be careful with parentheses. But if you copy down what I typed in, type it in just like that. Just change R to whatever R has to be, and change the first term to whatever the first term has to be. So if you do your parentheses just like that, you'll always be okay. So any questions on that? Okay, we're not always going to have to graph it. We're going to come up with a way, we're going to come up with a formula. So you could just do it on paper without a graphing calculator. But let's try, actually that's the one we just did. Let's try this one. Okay. In order to write our formula, I need 2 things. What's the first term here? 4. And what's R? 3. So the formula that would generate my equation for the partial sums would be the first term times what would go in the top. Yeah, I'm going to use X just because on the calculator that's what I have to use. And in the bottom?
2.
1 minus 3, which is negative 2. All right, now that I have it typed in, it shouldn't be that bad. I just have to change the first term to a 4 and change r to a 3. Technically, I don't even need parentheses around the 3 anymore because it's not a fraction, but it's not going to hurt to leave them. Okay, so I'm going to graph it. I'm going to reset my window. Let's go 0 to 10. I'm going to set my Ymax at 50. And let's hit graph. Okay, looks good.
Because your denominator is 3 instead of negative 2.
That could be, and the fact that I left it on the dotted mode. Could be both of those. And that should be negative 2. Does that look good now? Let's check it. Okay. What's happening?
Approaching 3.
It's approaching what?
3.
You think so? Does it look like it's stopping?
Is it approaching?
Remember, that's a Ymax of 50 on the screen right now. Let's want to set it a little higher, see if it stops going up. Let's try 200. So what do you think is happening?
Infinite solution.
Yeah, it's not converging. Okay, this is not adding up to anything. It's just when you keep adding numbers, it just keeps getting bigger and bigger. So if you add up just the first term, what would you get? Just the first term? 4. You just get the term itself. The first 2 terms, when you add those together, you get 16. When you add the first 3 terms together, you get 52. Just by looking at the first 3, I can tell this is not converging. It's getting worse. Okay? First 4 terms now is 160. If you add the first 15 terms, it's big. Okay? It's getting bigger and bigger and bigger. So we can't write an answer for this. Well, we can, but I haven't told you how to write it yet. So in example 3, as x gets bigger and bigger, this graph doesn't have a horizontal asymptote. It's just going up. It was at like 2 billion or whatever that number was in the calculator. There's no horizontal asymptote. So the way you write the answer is to say that the series, okay, the sum that you're trying to find is divergent. Or you could say diverges. So diverges means that it does not add up to anything. It just grows and grows and grows. Now, one thing I didn't mention with a sequence is you can use the same term with sequences. You can say a sequence is convergent or a sequence is divergent. Here's an example of a sequence, okay? Not a series, just a sequence that's divergent. The reason that sequence is divergent is because look at the pattern. Does it look like the numbers are getting closer and closer to a value? No, they're just doubling each time. They're just growing and growing and growing. But let's look at something that's like the opposite of that. Let's look at 2, and then let's go 1, 1/2, 1/4. What am I doing each time?
Getting closer to 0.
And I'm taking, because I'm taking half of it. Take half, half, half. And each time you take half of a number, the next one is a little closer to 0, and then a little closer, and then a little closer. But will it ever reach 0? No. The only way you can reach 0 is if the top number in a fraction is 0. Right? No matter if you start with any number, if you keep taking half of it, it'll get smaller and smaller, but it's never going to reach 0. Okay? It'll get very, very, very small. So this would be an example of a sequence that converges. Specifically, it's converging to the number 0 because it's getting closer and closer to 0. This sequence diverges. It's not getting closer and closer to any value. Okay? So we can use the term convergent and divergent with a sequence, or we can also use it with a series. Okay? And it's the same idea. Is it approaching a value? If it is, tell me the value. If it's not, just write divergent. So sometimes a geometric series converges. We did one earlier. It looked kind of like this. Kind of leveled out. And then the one we just did before that, it didn't level out. It just kind of just kept going up. So sometimes they converge, sometimes they diverge. There's a way to tell just by looking at the problem. Did anyone see the difference between this? There's a big difference between that one and this one. Put them on the board at the same time. Actually, if you want to compare similar things, look at the two things that are circled, that and that.
It's,
What's the difference?
when you multiply by a fraction.
Right. This one, if you take a fraction as your common ratio, remember this is R. If you multiply by a fraction over and over and over, a fraction less than 1, what happens to your number? It gets smaller and smaller and smaller and smaller. And if you keep adding a number to a series that is smaller and smaller and smaller and smaller, eventually you're adding a number that's so small, it doesn't even make a difference. That's the idea. Here, you're multiplying by a number bigger than 1 each time you add something. What happens to numbers if you multiply by something bigger than 1? They just keep getting bigger and bigger and bigger. So every time you add something, you're adding something bigger and bigger and bigger. So all you have to do to figure out if something converges or diverges is look at what I just circled in blue. If it's a number that's a fraction, 1/3, 1/2, it will converge. If it's a number greater than 1, it'll diverge. So based on that idea, I was going to have you graph each one of these one at a time and look at them and see what happens. Which values of R here would this graph converge for? A and D. This would converge. This would converge. Slightly different question. Which one would converge faster? Like which one would start to approach the value it's going to approach quicker? A. Because that's making the number smaller faster. Okay? Like if you multiply a number by, like watch what happens. If I take the number 10, multiply it by 0.9, it got a little smaller. A little bit smaller. It's getting smaller, but it's not getting smaller very fast. It's still above 1. Now it got below 1. But I had to press it at least 15, 20 times. Versus if I take the number 10 and multiply it by 0.5, it's getting smaller. I'm already below 1. And I only pressed it like 4 or 5 times. Okay? So we can talk about things converging faster or slower. How about here, 1.1 and 1.2? Those values of R would cause your graph to do what? It would diverge. It would approach infinity. Which one would diverge faster? 1.2, because that's making the number bigger a little faster than 1.1. But the point is they would both diverge. And then if it's equal to 1, we don't really talk about that, because if you raise 1 to a power, it doesn't do anything. 1 to the 50th power is still 1. So then it doesn't really do either. Okay? So this is the idea. If you have an absolute value of r less than 1, converges. And I say absolute value of r less than 1 because r could be negative a third. Whether you multiply a number by negative a third or positive a third, it's still making the number smaller. If you do positive a third, you get a graph that looks kind of like that. If you do negative a third, what happens when you raise a negative number to a power?
Well, depends what power.
Depends on the power. So if it's, think of that as your x-axis. If it's an even power, what do you get?
Positive,
What if it's an odd power?
negative.
Negative. The next one would be even. The next one would be odd. Even, odd, even, odd, even, odd. So what happens if you have an r value that's negative, but still between -1 and 0, you get this kind of alternating behavior where it alternates closer and closer and closer to your asymptote. If you tried to graph that, it wouldn't work. The calculator can't even graph something like that. Okay. And what it converges to is actually a pretty simple formula. It's kind of like the formula we learned yesterday. You have the 1 minus r in the bottom, and you have the first term, but you don't have this 1 minus r to the n. That's gone. Okay, so this, let me just write down exactly what this is. This is the formula for the sum of an infinite geometric series. Now, I mentioned geometric. We didn't really talk about arithmetic. If you add up infinitely many terms in an arithmetic sequence, what would happen?
You wouldn't be able to solve it.
Why?
Because it keeps adding.
Yeah, when you have an arithmetic sequence, the terms in it, you just keep adding. The terms never approach a value in an arithmetic sequence. They just keep getting bigger and bigger and bigger and bigger, or they just keep getting smaller and smaller and smaller and smaller. So that's why you cannot add up infinitely many terms in an arithmetic sequence. That doesn't work. Okay, so here's a geometric sequence. How do I know this is geometric and not arithmetic? It's being multiplied. Okay, you have the formula for the formula that they want you to use has 5 times something to a power. So we need the first term, and we need r. If you forget how to figure out the first term, you can plug in 1 for k. But we should know the first term just by looking at it. Where is the first term always? Yeah, it's right in front of the fraction that's, or the number that's to the power. So the first term's 5. What's r here? 1/2. So before I even try to plug this into the formula, is this convergent or divergent? Yeah, how do you know? Yeah, that's the key right there. R is less than 1. Right? So each time you add a number, it's going to be half, in the sequence, it's half of the one before it. So it's going to get smaller and smaller. Okay. So what's our formula to add up infinitely many terms?
5,
Yep.
1 minus 1/2.
What's 1 minus a half? 1/2. And what's 5 divided by a half? careful, not 5 divided by 2.
7. 10. Oh, no, 10.
10.
No,
So, what we just did there is we just added up an infinite amount of numbers using a formula, and we got an answer of 10. So if you were to graph this one, it would look something like that. And it'd be a horizontal line at y equals 10. Okay, any questions on that? Everyone's okay with that formula? All right, so last thing I'm going to show you has to do with the test tomorrow. If you watch the review video, it pretty much covers everything except today. All right, so I think it was like 30, maybe in 35 minutes, I'm not sure. But it's a shorter video and it covers everything we did Monday, Tuesday, and Wednesday. But something in the video I want to mention is something like this. Okay, I'm going to do a specific example. If I wanted to do that out, how do I do it out? What's my first step?
Plug in.
Plug in what? Plugging in 4 is the last step. So the directions here we just say to like expand. Because it's only going 1 to 4, they want us to expand it. Expand it doesn't mean to split it up. Expand it means to actually find the number that's the answer.
You plug in 1
Yep, plug in 1 for
K.
For K.
Do that all the way up to 4.
And do that all the way up to 4.
And
So
half together.
if you plug in 1, what do you get?
3.
If you plug in 2,
5.
and then 3, and then 4. 9. Okay, so that's the answer. 3 plus 5 plus 7 plus 9. So 3 and 5 gives me 8. 8 and 7 gives me 15. And 15 and 9 gives me 24. I want to show you something slightly different, but same. It's going to come out to the same answer. I'm going to start at 0. I'm going to go to 3. And I'm going to do this. Let's see if it comes out the same, and then I'll explain what I did. Let's start with 0. What's 0 plus 1? 1 times 2?
2.
Plus 1. 3. 1 plus 1?
2.
2 times 2?
4.
Plus 1?
5.
5. It's coming out the same. And it will. You get exactly the same thing. Did anybody see what I did to rewrite the top one like the bottom one? Okay, the name of what I did is called reindexing. I adjusted my index to start at 0 instead of 1. And I had to adjust 3 things. The bottom, the top, and the right-hand side. Alex?
It looks like you took one term from the top and then added it to the bottom.
So I took 1 away from the top. I took 1 away from the bottom. But if I take 1 away from something, I have to balance it somewhere else. Yeah. I have to balance it right there. So another way I could write the same thing would be if I did something like this. Let's start at k equals 2, and let's go to 5. What did I just do to my index? So whenever you increment from your start to your finish, you always go by ones. So you're going to go 2, 3, 4, 5. You can never change what you're incrementing by. But you can change where you start and where you finish. So what did I change about my start point? What did I do?
You increased by 1.
I increased it by 1. I changed my start point. Think of it as I did a plus 1 to it. So if I did a plus 1 on those two numbers, What do I have to do to the k to balance it? Alex?
Don't you have to subtract one?
I have to subtract them to keep that balanced. And you could try that. Plug in 2. 2 minus 1 is 1. 1 times 2 is 2. Plus 1 is 5. That's exactly what we had if you look back. Right? So what that's called is it's just called reindexing. You're just adjusting where your index starts. And of course, if you wanted, you could FOIL that out and actually get what the formula is. So that one's 2k minus 1. We started with 2k plus 1. And that one is 2k plus 3. So the reason I showed you that is because if you get something like this on the test, and it's a multiple choice question, and you see that, they're the same thing. So if your index is off by 1, just adjust it, and you'll see your answer there. You might have to distribute it, but that's the idea. So any questions on that idea? And if you want to see another example of that, just check out, you could just check out the video. If I have a sequence that does something like this. It's alternating. Positive, negative, positive, negative. There was something I said you always put, if you want to cause a sequence to alternate positive, negative, is something you put in there. It doesn't change the value. It just changes the sign. So in fact, let's try to write a formula for this sequence. What's one thing that would definitely have to be part of it? Yep.
A negative exponent, or no, a negative number, that's power.
A negative number to a power. So I would do this. I would start with that.
And doesn't the number, it has to be to the power of something odd.
Yeah, the first one, you might have to adjust this, because the first one, if you plug in 1, you get negative 1 to the 1. What kind of number is that? Negative. Now I just adjusted it by 1. Now let's plug in 1. What's 1 plus 1? 2. What's negative 1 to the 2? Positive or negative?
Positive.
That's now positive. Now if I plug in a 2, what's 2 plus 1? And what's negative 1 to the third? Negative. So I've taken care of the sign part. Positive, negative, positive, negative, positive, negative. Now I need to take care of the number part. Right? What's happening each time?
The absolute value is increasing.
True, the absolute value is increasing,
It's doubled.
and it's doubling. I know it's alternating positive, negative, but you can forget, you've already done that. What number is connected with doubling? 2. Let's try that and see if it works. Let's plug in a 4. What's 4 plus 1? 5. What's negative 1 to the 5th? Negative 1 times, I'm doing 5. What's 2 to the 5th power?
Oh, wait.
2 times 2 times 2 times 2 times 2.
36.
Well, what's that? 32. And 32 times negative 1 is exactly what we wanted. So that's it. We've come up with the formula. So that's how I handle one that's...
It's positive, there should be negative there too.
So do we have the right formula? Let's see, did I do it right? Positive, negative, positive, negative, positive, negative. So if you plug in 5, let's just check it. Oh yeah, what's 5 plus 1? 6. I don't know what we did here. What's negative 1 to the 6th?
1.
Yeah, it should have just been a 1. So that is correct. I think we just plugged it in wrong. Right? So there's your formula. So whenever you have something alternating, try to look at it in 2 parts. Figure out the negative part first. So it's usually negative 1 to a power. If you have to adjust it, because it starts negative, positive, all you do is go like that. And now what that would do is it would change the signs of everything. That'll put it back the way it was. Okay, so you'll see a problem on the test where the sequence alternates like that. Okay, any general questions about the test tomorrow? There's 2 questions on matrices. The first one, I give you a matrix. The second one is a word problem that you have to set up. Then the rest of the test is on sequences and series. Okay, so you should know how to tell if a sequence is convergent or divergent. If a series is convergent or divergent, we did that today. How to add up terms in a series. What else? How to find an explicit formula. That's exactly what we just did here. How to find a recursive formula. So recursive formula for this problem would just say, take the one before it and multiply by -2. That's it. Okay, so if I wanted to write this recursively, it would be like this. -2 times the one before it. Make sure you know the difference between an arithmetic and a geometric sequence. And I think that's pretty much it. Okay, so any questions on the stuff I just mentioned? Okay. All right, so the homework tonight, same homework page as last night, 601. And it's 21, 22, 29, and 30. Then it kind of skips around a little bit. 33 to 35, 38, 39, and 42 to 44. Okay, so we'll look at that tomorrow before the test. Okay, don't forget, I won't be after school today because I stayed after yesterday.